Okay, so this video clip is looking at position vectors, and then there'll be a couple of examples that bring together everything from the previous couple of videos as well about unit vectors, position vectors, force vectors, finding resultants and things. The key idea of position vectors is that they're literally describing how you get from A to B, or from B to A. So it's just the difference in the x, the difference in the y, and the difference in the z. So for example, my position vector, which I'd call r, from A to B, would just be my x-coordinate of B minus my x-coordinate of A, I, plus my y-coordinate of B minus my y-coordinate of A, J. I should probably put brackets around these. I'm going to move on to the next line just so I don't run out of space, plus my z-coordinate of B minus my z-coordinate of A. Okay. And that is a position vector. Not particularly difficult to use, but it will be useful in finding unit vectors later on. What you can then do with that is you can work out, okay, how far is it from A to B by using Pythagoras, squaring these various elements and the square rooting. What's probably easier is to remember that the unit vector that you find with that will point in the same direction, so you can then start to work out how a force acting, how much of a force acts along that particular line. If we look at the example in lecture 2 on slide 45, about 420 Newton force acting along cable AC, I'll just very briefly draw it and we'll go through how you'd work it out. Okay, so this diagram has two forces in it in the lecture. The diagram is actually one from a textbook which has several questions to do with that particular diagram, but we're only interested in force C in this particular example. So you haven't got much information, but you can find, if we call this point A is in the diagram, so I missed some details in this point C, you can start to find some details about some position vectors. So from R, A, C, the position vector, how you get from A to C. Well, along in the x direction, so from the origin to in the x direction, you're moving 2 meters, so 2I. In the y direction, you're moving 3 meters to get from A to C, so that's plus 3J. And in the z direction, you're moving down from A to C, and you're moving 6 meters. So that's minus 6k. What we can then do is we can say how far it is from A to C. So how long cable AC is, that's the magnitude of RAC, which will be 2 squared plus 3 squared plus 6 squared square rooted. And I've ignored the minus because if you square a minus and then square it, you get rid of the minus anyway. So that will equal 7 meters. So that cable is 7 meters long. But we also know that a unit vector, so the unit vector A to C, the proportion of x, y's and z's to get A to C, that's going to be equal to a vector over its magnitude, so RAC over the magnitude of AC, which will be 2/7 I plus 3/7 J minus 6/7 K. And hopefully you'll start to realise why unit vectors are worth looking at as we go through these. So now we can get a force vector, because a force Cartesian vector, for AC in this case, is equal to the force AC times by the unit vector AC. So the magnitude of the force times by the Cartesian vector that describes the direction it's acting. So we're literally going to put 420 2/7 I 3/7 j minus 6/7 k. Multiply that out, and we're going to get our Cartesian vector for force. So 120I plus 180j minus 360k. So that answers the example question. If you pause it now and have a go at the group problem solving activity in lecture 2 on slide 48, and then replay or play the next section of this video, and I'll show you how to go through it. So you should now have had a go at the group problem solving activity on slide 48 of lecture 2. It's a flagpole with two forces, FB and FC, very similar to the previous example, but you have to do slightly more with it. So I'll just draw it and then we'll go through it. So this clearly isn't as well drawn as in the question. So I'd recommend you actually look at the question if you want to see the proper diagram, which will probably be a little more help to you. We've got two forces acting, 700 newtons in cable AB, or cable AB, and it's 560 in cable AC. And we're asked to find the resultant force and then the resultant direction in terms of alpha, beta and gamma. And so same principle as before, just two forces to deal with, and then we add them together. So it's bringing together two different examples. So how do I get from A to B? Well, from A to B, in the x direction, I've got to go 2 meters. In the y direction, I've got to go 3 meters, and I'm actually going backwards because positive y is that way. They've labelled the y on the positive end, that's the standard practice. So going backwards 3 meters, and in the z direction, going down 6 meters. So my distance, which is the same as before coincidentally, whoops, RAB, not RBB. RAB is going to be 7 meters. And similarly I can do RAC, so same as before, apart from I'm going 2 meters in the y direction. 2 meters in the y, yes, I am going 2 meters in the y direction and 3 meters in the x direction. So my x and y swap places. I'm also going positive direction for both of those for RAC. So 3I plus 2j. I'm still coming down, so minus 6k. So RAC is the same numbers, so it'll be 7 meters as well. So both those cables are 7 meters long. I can then find a unit vector. So the unit vector for AB will then be 2/7 I minus 3/7 j minus 6/7 k. And then my force AB as a vector will be 700 times 2/7 I minus 3/7 j minus 6/7 k. So that's going to equal 200 I minus 300 j minus 600 k. I'll just jump to my next slide. FAC is going to be my unit vector AC times by the magnitude of AC. My unit vector of AC, I'm going to take my position vector for AC, which is this one just here, and my magnitude of AC, same as before. So my unit vector will be 3/7 I plus 2/7 j minus 6/7 k. So then my force vector will be 560 times 3/7 I plus 2/7 j minus 6/7 k. So if I multiply that out, that will equal 240 I plus 160 j minus 480 k. If I then take my FAC Cartesian vector from here, and I take FAB from the previous slide, the 200i minus 300j minus 600k, I can add those together, add the i's, the j's and the k's, so I'll get 440i minus 140j minus 1080k. If I then want to find the magnitude of that, I'll square and square root. So that will give me a magnitude of 1175 newtons. If we then remember this piece and my total magnitude for the next slide, so not that bit, don't need that for the next slide. My alpha angle will then be the I component of my resultant force, so 440 will be the inverse cosine of 440 over the total magnitude of 1175, which equals 68 degrees. Beta will be the inverse cosine of the the j component, which is minus 140, divided by the total magnitude, which is 96.8 degrees. My gamma will be the inverse cosine of the k component, which is minus 1080 over 1175, which is 156.8 degrees. So this video explained a couple of different things using some of the position vectors that we've looked at, putting it with other things like unit vectors and force vectors to solve more complicated problems. And that all relates to the middle part of Lecture 2 on forces.